Hello and welcome to Lesson 2. This is the first of two lessons where we're going to revise the flow behaviour of time-independent fluids. In other words, fluids that don't possess elasticity. The approaches that we'll develop in these two lessons will allow us to estimate, for example, pressure drops in processing systems, as well as giving us a framework to examine the flow of more complex fluids in later lessons. Polymer melts and polymer solutions are typically very complex materials, but during any analysis we must try and use the simplest model that gives us a result that is fit for purpose. So perhaps this underlines the importance of not only knowing the problem we want to solve, but also the desired accuracy of the answer. If we think about time-independent fluids, the simplest fluid description we can find is that of the Newtonian fluid, one that has a constant viscosity. We can then think about fluids that are generalized Newtonian. These fluids have a viscosity that depends on the shear rate, but still no time memory. Generalized Newtonian fluids can be used in a number of approximate analyses that can be very, very useful in polymer processing. Before we start talking about generalized Newtonian fluids, however, we need to make sure that our knowledge of Newtonian fluids is sound. So that is what motivates this lesson. In this lesson, we'll be revising aspects of Newtonian fluid flow and also laying the groundwork for looking at flows that may not be purely one-dimensional, but more about that later. Let's start here by examining the level of knowledge that I'm assuming that you'll have. If it has been a while since you've used this knowledge, fear not, as I'll also be pointing you towards some material that can be used for revision. So, let's colour in this motivation a little more. Let's say we're trying to design or troubleshoot an injection moulding line. The injection moulding line, maybe injection mould rubber plastic ducts. There we go. Maybe what we want to do is to try and estimate to 10 or 20%, enough to specify a machine, the pressure required for moulding. And so we need some knowledge of the polymer, the flow path, and the various pressure drops that are involved within that. And maybe it is just literally an approximate answer we need because we've got machine A or machine B. There is not a great deal of granularity between these two. And so all we need is a technique there that allows us to get a quick answer that is fit for that purpose. We may have a different problem. Say, for example, we move back to our fibre spinning line that we looked at in the preamble to this lesson. Now, for those of you who have studied rheology, you'll know that for a viscoelastic fluid, that stresses are built up as a function of flow and then released over time once that shear strain rate is reduced. So that can produce a number of effects, for example, extradate swell, and we may want to estimate the extradate swell of a material. And in order to do that, we need to estimate the stresses that are built up as a function of the flow beforehand. So, again, maybe we can find a way to do that that gives us an answer that we need quickly and simply that is fit for purpose. Another example, we may, for example, be operating a film blowing line, and we might be, for example, producing biodegradable packaging. Now, we want that packaging to be strong enough over the first use period, maybe weeks or months, to ensure that whatever's contained within inside that packaging, for example, rice or pulses or some other food, actually doesn't leak out and puncture it. So we need to be able to think about orientation development, and we know now that that's a function of extensional deformation, and so we might want to be able to estimate that degree of extensional deformation both in the melt and in the solid phase. So what we want to have is a set of analyses that we can do that allows estimates of these that are fit for the purpose of the answer we're trying to get to. And so knowledge of fluid flow, and therefore stress and strain rate, allows these factors to be quantified. So we're going to start at the simplest point. We're going to start by revising Newtonian flow. It's acknowledged that not many processes you'll meet in the polymer processing industry will have Newtonian fluids, but this lays the foundations for looking at more complex fluids later on. So let's have a look at some of the assumed knowledge that you must have in order to do this. So let's start with a bit that everybody loves, and that's the mathematics. So when it comes to vector calculus and the manipulation of tensors and vectors, I'm expecting that you should be able to, for example, take a Laplacian of a vector field, or maybe even a divergence of a vector field. Or perhaps you might want to estimate the magnitude of a tensorial quantity, for example, the magnitude of stress. So you need to know something about the double dot product of these two entities. Or, for example, we might want to take the dot product of two vectors together, so v dot u. So if you're looking at that screen now and thinking, oh yeah, I'm comfortable with that, that's fine. If you're looking at what I've put on the whiteboard and going, oh, then don't worry, because there's a couple of videos that I've linked there, and I'll put these links in the show notes, that I recommend that you go and watch. And these two videos concern matrix and tensor operations, and also a very brief guide to vector calculus. Okay, let's move on. Another piece of assumed knowledge is using momentum equations. And so we can think about two momentum equations that we know and love. There's Cauchy's momentum equation, there's the Navier-Stokes equations. Let's start by thinking about Cauchy, since it is the most general statement of conservation of momentum in a continuum fluid. It's simply, effectively, a statement of force equals mass times acceleration. And it looks a little bit like this. On the left-hand side, we have the forces that give rise to a change of momentum on the right-hand side. And so there's body forces, there's surface forces, and then there's accelerations. And you've got time-dependent accelerations, and you've got spatial accelerations. And we can more compactly write Cauchy's momentum equation using the convective derivative, as I've written there on the board. So again, if you're happy with all of this, great. If you're not happy with all of this, and you're looking at it thinking, I've forgotten what those terms are, don't worry. There, again, I've put some links to some videos to watch that will tell you all about conservation of mass and the derivation of Cauchy's momentum equation, so you can get back up to speed with what these terms mean, how you use them, and more generally what this equation is describing. So, sticking with the theme of momentum equations, we have the Navier-Stokes equations, which describe conservation of momentum for a Newtonian fluid. And so they start with Cauchy. And Cauchy's momentum equation, which we looked at on the previous whiteboard, is written as so. And it is just a few lines of manipulation that is required to get to the form of the Navier-Stokes equations, which I've just put there. The two key things that happen are that we're making an assumption about the nature of the surface forces within the fluid. They're hydrostatic surface forces, that's the PI term there, I is the identity tensor, and tau is the stress due to deformation. And I've also put what that deformation stress is. It's the gradient of the velocity field plus a transpose of the gradient of the velocity field. So it is time independent, and it is that entity we call the shear rate, and it is pre-multiplied by a constant, mu, which is our material viscosity. And so the Navier-Stokes equations make the assumptions that the material we have is of constant viscosity, and there's no time memory. Again, if you're looking at this and thinking, oh yeah, I'm happy with that, brilliant. If not, don't worry, because I've got a video there that explains all about the Navier-Stokes equations and where they come from and what the different terms mean. And I'll put that link in the show notes of this video. Now, it's all very well having these equations, but what we want to do is to set these equations up to solve a problem. So we can do that with either Cauchy, which we'll be doing quite a lot of, or the Navier-Stokes equations, which you've hopefully already done quite a lot of. And if we're doing that, we really need to make some simplifications, because the Navier-Stokes equations and Cauchy's momentum equation, as written, are three sets of coupled partial differential equations, and the Navier-Stokes equations in particular, and the Cauchy equations as well, have a nice nonlinearity in them, in that convective derivative, that v dot grad v term. And so we've got three coupled nonlinear partial differential equations that require solution. You can do that with computational methods if you want to include every single term, but very often a simple analysis will get us a very long way to getting an answer that might be fit for the purposes we desire. And so, for those of you who have recently sat the rheology course 640, I introduced a 4-step workflow to simplifying and then solving the Navier-Stokes equations. And so if you're looking at the Navier-Stokes equations there on the board and thinking, oh yeah, I remember how to do this. I can solve that for pipe flow. I can solve that for flow down an inclined plane. I could even think about solving it for a free surface flow. Then great. If not, again, don't worry, because here I've put some links to three videos that give you an explanation for how to calculate pressure-driven flow using Navier-Stokes through a 2D Cartesian geometry, draining flow, and pipe flow. And so if you're unfamiliar with using Navier-Stokes at the moment, do please watch those videos and revise how to do it. Okay, so let's recap a few key points. We're going to be using the conservation of momentum plus knowledge of fluid rheology to examine aspects of fluid flow in processing. So this revision of Newtonian fluid mechanics is the first step in allowing us to do that. The motivation for doing this is it's going to help us to understand pressure drops in extrusion systems or moulding systems, and also quantify shear rates and shear fields, which will allow us to calculate stresses and estimate stress-induced effects, for example, orientation or maybe some instabilities. So what we want to be able to do is to use this knowledge to solve problems. And when solving a problem, don't forget, always ask yourself how accurately you need to know the answer. If it's within 20, 30, 40, 50%, very often an approximate analysis will get you a very long way. There is a tendency I've seen for people to try and dig in too deep too quickly, to go to a fully computational solution which takes a lot of resource, a lot of overhead, and a lot of time to answer a problem that could be usually done on the back of an envelope. So go into problem solving, please, with your eyes open, and always ask yourself, how accurately do I need to know this answer, and what am I using the data for?